So now we will start with a new topic. So this we did in the last lecture. So now we are starting with a new topic. So what is the new topic? We want to design a BCD to 7-segment decoder. So this is our objective. We want to design a BCD to 7-segment decoder. Okay. Now, if you look at this problem, so now can you see here? So this is the so what is the BCD to 7-segment decoder does? It accepts an input of BCD digits. Okay. So what is my input? So now can you see here? This is my input. Can you see here? What is my input? Tell me. So BCD to 7-segment decoder. What's my input here? Anyone? What is my input now? Yes, anyone may speak, please. Please talk. What is my input here?
A, B, C, D.
My input is BCD. Okay, so this is a BCD code. Okay, okay. Now if you look at the BCD inputs, how many inputs are there? So there are how many inputs? So this is n inputs. So this is 4. We have 4 inputs. If you look at the block diagram. Okay, now how many outputs are there? Can you tell me how many outputs are there? Help me.
7.
7 outputs. So we have 4 inputs and 7 outputs. Now this is just looking at the block diagram. So from the block diagram level, so we have 4 inputs. The input are A, B, C, and D. Okay. Now if we have 4 inputs, so now can anyone tell me how many combination do we have now? How many combination do we have? How many? Can you tell me? So we have to score 4, which is actually 16 combination. Since it's a BCD code, okay, now if the code ranges from 0 to 9, so can you see if we say if the code ranges from 0 to 9, valid BCD code or invalid BCD code?
Valid.
It's a valid BCD code. And if the code is between 10 to 15, what does it mean? Help me.
Invalid.
So it is an invalid BCD code. Okay, now what is a 7-segment display? Now can you see here? Now can you see? Now the output is 7-segment display. So now if you look at here, so my output is now 7-segment. So this is a 7-segment display. So this is 7 segment. There are 7 segments. Okay, so this is my segment A. This is segment 1. This is my segment 2. Segment 2. This is segment 3. This is segment 4. This is segment 5. This is segment 6, and this is segment 7. Got it? How many segments do we have? We have 7 segments. So these are 7 segments. So what is the name of the first segment? What is the name of the first segment? Can anyone help me? Yes. Anyone help me? Number 1. Look at here. A. So this second segment is B. This is C. This is D. This is E. And this is F. And this is G. Any question? Any question? Now if you want to display 0, so now can you see here? So we want to display 0. So now this is my 0 here. So this is 0, 0, 0. We want to display 0. So this is, if you want to display 0, okay, which segment should be on? Help me.
A, B, C, D, E, F.
And if you want to display 1, let's say I want to display 1 like this. Which segment should be on? Help me.
B, C.
Now let's assume if you want to display, let's assume we want to display 2. So now can you see here? This is my 2 segment. This is my 2 segment. Which segment should be on? Help me.
A, B, G, E, D.
A, C of D, E, F is of G. Any question? Okay. Now if you want to display 3. So now if you want to display 3. So now this is my 3. So this is my 3. Display 3. Which segment should be on? Help me.
A, B, G, C, D.
F and G. So these segments should be on. Okay. So for this problem, we need to draw the truth table. So now can you see here? Now we need to draw the truth table. Okay. So we need to draw the truth table. So basically now what is my input? So my input is A, B, C, D. Please remember now, can you see if you look at from the BCD to 7-segment display? So now what I'm going to do, I'm copying this and I'm pasting it here. So this is my, these are my inputs. So these are my inputs, A, B, C, D. So the A, B, C, D are my inputs. So now A, B, C, D are my inputs. So I'm making it the red color. So A, B, C, D is my inputs. This is my inputs. And now my outputs are, and I'm now using another color. I'm now using a green color. So now this color is A, B, C, D, E, F, and G. Okay, now we want to display 0. So now this is my 0. So this is 0. Please, how can we display 0? So this is actually, this is control 0. 0. Okay, now if you want to display 0, so 0, 0. Okay, 0, 0, 0, 0. So this is 0. Please remember, this is the code for 0. This is the BCD code for 0. So 0, 0, 0. Which segment should be on? Help me. A should be 1.
All of them except G.
All of them are 1 except G. Because this is A, this is B, this is C, this is D, this is E, and this is F. If you want to display 1, okay, now I'm using the purple color. So basically, can you see here? This is 1. If you want to display 1, so B is 1 and then C is 1. So now we can see here this is 1. So 0, 0, 0, 1, which is actually equal to 1. So B is 1 and C is 1. So B is 1 and C is 1, and all segments are what? 0.
0.
Now if you want to 0. Now if you want to display, let's assume you want to display 2. So now I'm using a different color. So now I'm using a black color. Okay, so now this you want to display 2. This is my 2. So this is my 2. So 2, what is the code for 2? 0, 0, 1, 0. And this is A and B and C, D, E, F, and G. So A is 1, yes. B is 1. Then, yes. C
C
is
is
0.
0.
0. D is 1. E is 1. F is 0 and G is 1. Any question? And then we can fill the truth table for all the possible BCD inputs. Any question? Any question? Is this clear or not clear? Clear? Okay. Should I proceed?
Yes.
Please speak in mic. Please speak in mic. Okay. So now if you look at here, now please look at here. If you look at here, so now basically now we have drawn the complete truth table. So now we have drawn the complete truth table. So now we have how many inputs are there? So this is actually 2 power 4, which is actually 2 power 4, which is actually 16 combination. Out of these 16 combinations, so these are the valid inputs. The green one are the valid inputs or invalid inputs?
Valid.
A valid inputs from 0 to 9. From 0 to 9. And the last thing it is, I'm using it the purple color. So this is actually, can you see here for purple color? So these are invalid inputs. And for all these inputs, valid, invalid inputs, we do not want to turn on any segments. So all of these are 0. So it means all segments are off or on?
Off.
Are off. Okay. Now can you see here? Now this is the code. So now if you look at here, this is the code for what? This is the code for 0. This is 1. This is 2. This is 3 and 4 and 5 and 6 and 7 then 8 and then 9. Can you see here? This is the code for 0. So for 0, now if you look at 0, only G segment is off. So for 0, can you see this is only G segment is off for 0. And for 1, can you see here for 1? For 1 segment, can you see here? So now this is B and C are on. B and C are on. So for 1, B and C are on. Any question? And similarly, you draw the truth table for a BCD to 7 segment. Any question? Any question? Should we proceed? Okay. Now if you look at this problem, so okay, now let's assume what I'm going to do. So now if you look at this problem, so you can say, so control C, and then I can paste it here. What I'm going to do now, I'm going to copy this, and I'm going to paste it here. Okay. This is important. Please remember this is important. So please don't consider it. So this is I'm copying it this, and then I'm pasting it here. Now, if you look at here, how many inputs are there? Please look at here. How many inputs are there? Anyone may answer. And how many inputs are there? Yes.
4.
4 inputs.
4 inputs. And how many outputs are there? Help me.
7.
Now we have, if you have 4 inputs, how many combinations we have? Yes. 2 to the power 4 is equal to 16 combinations. Okay, now there is 2 to the power 16 combinations. Okay, how many K-maps do we have? How many K-maps? And can you answer me? How many K-maps do we have? How many K-maps? Yes?
1.
No. Because we want to solve for A, B, C, D, E, and F, and G. How many K-maps do we have? Because there are 7
Okay.
outputs.
7.
We have 7 K-maps. Okay, we need 1 K-map for A, 1 K-map for B, 1 K-map for C, 1 for D, 1 for E, 1 for F. So we need 7 K-maps. And we need each K-map for A, B, C, D, E, F, and G. Any question? So we need 7 K-maps. Okay, now each K-map consists of how many entries? Help me. Can anyone help me? Yes?
16.
16 entries. 16 entries. Because this is 2 to the power 4, so this is 16 combination. So these are 16 combinations. Each make a map consists of 16 entries. Any question? Any question? Okay. Now, what I'm going to do now in the next slide, what I'm going to do, so I'm going to make it more interesting now. So what I'm going to do, I'm copying this thingy, and copying this thing. Control C and Control V. And now we have the truth table now. We have the truth table. Now, since we have the truth table, and we want to draw for segment A. Now, please look at it. This is very important. Please, I'm telling you, this may be the question in exam. This may be the question in exam. So I need your attention here. Okay. Now, if you do for this, can you see here? This is my A. Now I want to for A. Now this is my A, and now okay. If it is my A, so this is equally 0. Then 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So can you see what is now A? So can you see if you want to solve for segment A? So this is actually sigma M. What should I write? Help me. Help me.
0, 2, 3, 5, 6,
0,
7, 8,
2,
9.
5, 6, 7, 8, and 9. Because we are all interested in one. So we are why are we doing this? Because we are all interested in one.
Plus sigma D, yeah.
One, and one. Any question? Any question?
Professor, isn't A also plus sigma D?
A what? Sigma what? D?
Yeah, from
No.
10 to
It's not sigma D. Because we do not want. So from 10 to 15, all of them are what?
0.
Zero. So is it a don't care? No, it's not a don't care. Because in the
Okay.
specification, if it is an invalid, so okay, so for an invalid input, so what for an invalid input, we want to turn off. So for an invalid input, so we want to turn off all the segments. Any question?
No, sir. Thank you.
So for this, that's the reason. For this, we do not need. So for this, we do not need. We do not need what? We do not need don't care here. Now let's assume if I want to solve for segments. So let's assume if I want to find the expression for. If you want to find the expression for, let's assume segment. This now this is actually. Can you see here? No, I can use a different color. I use a purple color. So now let's assume if I want to solve for segment G. G. Okay, what is now G here? Can you not tell me G is what? Sigma and what? Help me.
2, 3, 4, 5, 6, 8, 9.
This is actually 2, 3, 4, 5, 6, 8, 9. Any question? And similarly, we can solve for B, C, D, and this we can do. Any question?
No, sir.
Again? Okay. Now what we are going to do? Now this is important. This is important. Now can you see here? And then since you have this, so now I'm going to do. So now I'm copying this. Control C, and then I'm control paste. Okay. Now what I'm going to do? Now what I'm going to rub this up. Now, can you see here? Now we have A. Now we want to solve for A. So if you want to solve for A, and remember in the Carnap map. So now we have in the Carnap map. So now this is my Carnap map, and I want to solve for A. And for please remember, now for A we are using the red color. Now you're using the red color for A. Okay. Now please remember, if you do solve for this red color, so now can you see here? So now this is the KMF for A. And remember the KMF. Okay. What are my input? My inputs are, please, these are my inputs. Remember, these are my inputs. This is input is A, B, and then C, D. So we start with 0, 0, 0, 1, 1, 1, and 1, 0. Again, 0, 0, 0, 1, 1, 1, and 1, 0. Okay, please remember what is the number? 0, 1, 3, 2. Then what should I do? Add 4. What is the number? Help me.
4576.
7, 6. And then I add 4 to it. Then 10, 11, 9, and 8. And then I add 4 to it. 12, 13, 15, and 14. Okay, now we want to solve for A. Now we want to solve for A. So this is A, B, and C, D. So this is 0, 0, 0, 1, 1, 1, and 1, 0. 0, 0, 0, 1, 1, 1, and 1, 0. This is 0. So 0 is 1. And then 2 is 1. This is 0, 2. This is 0 and 2. So please remember, this is 0, 2 is 1. 3 is 1. Okay. And then we have 5 is 1. Then 6 is 1. Okay. And then what? 7, 8, 9. 7, 7, 7 is 1. 8, 9. It is 8, 9, 8, 9. Got it? So can you see here? These are how we do it. So please remember, this is my 8. This is my 8. Look at the color coding. This is my 8. Where is my 9? So let's assume if we have the purple color, so this is my 9. Any questions? And you fill all the ones. How many ones are there? 1, 2, 3, 4, 5. So these are 1, 2, 3. So these are how many ones? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Here, 7. Any question? And similarly, we can draw the KMF for G. Any question? Any question? Should we proceed? Okay, now what we are going to do? Now, can you see here now what we are going to do? Control C, and then I can see, now we can solve it here. Control C and paste. Now we are going to solve it here. So I can delete the whole thing now. Okay, now we want to solve for A. Okay. How many groups do we have? Can we combine some groups? Anyone? Yes. What is the biggest group now?
The 4 in the top right corner.
The first group. Now, if you look at the group level, I can delete this and now I can delete this. Okay. What is the first group? Help me. Yes. I can now use the green color. So this is my first group. Any question? What is the other group?
8, 9.
Now, can you see here? Now we also have another group. The purple color. Yes or not? Because you know this is. Yes or no?
Yes.
And then we have another group. So we have another group. So I can use this light blue color. So this is the other group. And then we have another group. What is the other group? So maybe I will use the black color. So now this is the other group. So what is the expression now? Now for the green one. What is the expression for the green one? Can anyone tell me the expression for the green one? Yes.
A bar C.
A bar C plus. Now I want to do the expression for the black one. A bar B. So you can see here A bar B and then B plus. Now I want the expression for the light green one, the light blue. So the light blue, it is actually A B bar, B bar, and then C bar.
C
And
bar.
then I want to find it. And then I want to find the expression for the purple one. This corner, this thingy. So this thing is actually what? Help me. B bar, B bar.
B bar, C bar, D bar.
Very good, very good. So this is now the expression. So similarly, we have found expression for A, then we can find expression for B, C, D, E, and F. So we can. So how many KMF we have? We have 8 KMF. So can you see here? So now can you see here? Now these are 8 KMF. So these are the KMFs that I already draw it. So this is the thing. So this is the expression that I derived. Can you see here? Now, please look at the color. So this color is this thingy. This color is this thingy. This color is this. Look at the color coding. Similarly, we have the KMF for B. So for the KMF of B, so now we derive the expression for B using the truth table. Then we derive the expression for C. Then we derive. Okay. Now can you see here? Now what are the common terms here now? Can you see here? Now what I'm going to do is I'm going to copy this, and then I'm going to paste this here. If you look at this expression, what are the common terms here? Yes. Can you tell me what are the common terms here?
B bar, C bar.
So the common terms. Now I'm going to have the common terms in. Now I'm going to highlight this. So basically, can you see here? This is the common term. Yes. A bar B is here. Any question? Is there any A bar B in your place? What is the other common term? Yes.
B bar, C bar.
C bar is another common term. So this is my common term. So we will identify the common term. What is another common term? Can you tell me?
A bar, D.
Yes, A bar D is another common term. So A bar D is another common term. So A bar D is here, and A bar D is here. Can you see here? This is A bar D. So we have another common term. And similarly, is there any other common term? Can you tell me? Yes.
You didn't mark B bar, C bar in the first expression.
I mark B bar. Oh yeah. So yes. B bar C bar. Yes. This is the common term. And then we have another
There's
common term.
another one.
Can you tell me which is another common term?
Professor, there's another B bar, C bar.
Yes. This is also a common term. Clear? Any question? So now after going that, we identify the common term. Clear? And now we are going to. So this is the common term, which is the green color. So the green color common term is B bar C bar. And the black color common term, is A bar D. And we identify the common term. So can you see here? So now we are here. So again, we go for this, we find the expression. So we identify the common term. So now this here, we draw the truth table, we have to draw a common term. And then we extract this common term. So we can you see here this T1. What is T1 now? Now this is T1, A bar B. So this is A bar. The first common term, this B bar C bar is the second common term, and A bar D is the third common term. Any question? Clear? And then you can say A bar C plus T1, because this is T1, A bar B is the first term, so this is actually T1. So T1D, and we rewrite the expression. And then what is C? C is actually, this is the first common term, T1, this is T2, and now this is T3. Any question? Okay. Okay. What should we do now? Can you tell me what should we do now? Help me. What should we do now?
Draw the shared expression.
No, but we also need to find expression for which segment. We have only 3 segments now, A, B, C. What should we do now?
D, E, F, G.
F and G. So now what we do? So we draw the CAM for D, F, and G. So now we do. So now we have also the expression for, and then we expression all these common terms. So this is, we find the expression for D, E, F, and G. So these are all the logical expression for other expression D, E, F, and G. And now we have identified the common term. So we find all the common expression, and then we do all the tricks, and then we do this. Okay, now what I need to do? So now can you see when we derive all the expression, the common term expression? So now if you see, now what I'm going to do? So now basically what I'm going to do, copy, and then I'm pasting it here. Okay, and then we draw the logical diagram. So now what I'm going to do? So now I'm going to draw the logical diagram. I'm not going to draw this. So now I'm going to draw the logical diagram here. I'm going to delete everything now. Okay, now what is my E now? Now I'm just solving for segment E. What is E now? Yes, can you tell me?
T5
E,
plus T7.
My E, which is actually T5, which is the blue color. So the blue color. So now what I'm going to do? I'm now going using the blue color. So this is my blue color. Do I have a blue color? Yeah, I think so. This is my blue color. Okay, I can use the blue color. This is T5, and then we have T7, which is the green color. This is the green color. So I'm now using the green color. But what is T5? Can you see? We have already identified T5, and the blue color is actually B bar, C bar, D bar. Okay, B bar, C bar, D bar. So this is actually, we have an AND gate here, the blue color. B bar. Since we have B bar, so we have an inverter for B. And then we have C bar. And then we have what? D bar. Any question?
Professor,
Clear?
we can minimize it by pushing the knots through, yeah?
Because now the thing is, this is very important. So what I'm going to do, this is very important. This is very important. So this is what is T5? Can you tell me what is T5 now?
B
What is
bar,
now
C
T5?
bar, D bar.
No. Please remember. What is T5? What is T5 here? Please remember. What is T5? B bar, C bar, D bar. Clear? Okay. But now, can we write T5 is equal to what is T2 here now? B bar, C bar. We can write B bar. Then what? T2.
Okay.
So this is actually now my T2, and then we have B bar. So we have B bar. So we have B bar. So we need an inverter for B. And what is my T2? Please remember, what is my T2? So this is my T2. And T2 for T2, I'm now using a red color. So this is my T2. So this is my T2. Red color. So this
Professor,
T2
shouldn't
is
it
now,
be D bar? Because T2 is B bar, C bar, yeah.
oh yeah. You're right. You're right. So okay, C bar D bar is T2. Yeah. B bar C bar. So this is actually can I write here? You're right. So B bar C bar is T2 and D bar. Because what is T2? Now can you see here? Now I'm now using a red color. So B bar C bar is T2. So this is actually T2. So T5 is T2 D bar. So this is actually T5, which is T2 D bar. So now we have an D bar here. And then we have B bar C bar, which is T2. Now we have T2, and this is actually B bar C bar. So this is actually B bar and then C bar. Any question? And then it is T7. What is not T7? A bar C D bar. There is any other common expression in T7?
T0 D bar.
Hmm?
T7 is same
What is
as
now T7?
T0 D bar.
What is T7? Can you see here? What is T7 now? Help me. Now I'm using a black color. Now I'm using a black color. Okay. So T7 is what? Help me. A bar.
T0 D bar.
It is what? Help me.
T0 D bar.
Yes, T0. Because you can see here this A bar C is actually T0. T0 D bar. And then we can see T0. So now we have T0. So now we have this the black color, which is actually T7. T7 is T0 D bar. And since we have D bar, so we can use this thing, we can reuse this D bar. This is my D bar now. And now T0. What is now T0 now? A bar C. So T0 is now A bar and then C, and then we can okay. So we found the expression for E. Similarly, we can find an expression for F. We can find an expression for G. And if you go for all these things, so this is all the required expression. Clear? So now can you see here? This is my expression for E now. Can you see here? Here. This is now my expression for E. Look at here now. This is now my expression for E. And can you see here? This E is actually what? T7. This is T7. And this point is actually T5. Clear? And now this T5 is actually now we have this B bar, C bar, we already did. Any question? Any question? Clear? We derive all the expressions. So this is the same thing. This is the same diagram. So can you see this whole thingy is the same diagram. So what I'm going to do, so now can you see here? Now I can copy it here. Control C, and then I'm pasting it here. Can you see here? Control V. So now if you look at here, this is my E. It's the same thing or not? These are the same thing. Any question? Yeah. So similarly, we find all the expression for these things. So this is how we can design a BCD to 7 segment flow. So what are different steps? Okay, now if we if we have all the steps, what is now step number one? Let's assume we want to design a BCD to 7-segment decoder. We want to design a BCD to 7-segment decoder. Yes. What is my first step now?
And draw the truth table.
Yeah. So basically, what is my step? So this is my step. So step number one. So what are the steps? Step number one, we draw the truth table. So now what I'm going to do, where is the home and text box? Where is text box? Insert text box. Yes. What is my first step? First, we need to draw the truth table. This is my step number one. Then what should we do? In this example, we draw the truth table. We draw the truth table, number one. Then what is my step number two?
And draw the 7 K-maps.
Then draw the 7, because we have 7 output, the 7 K maps. Then we see what do you do? Logic minimization. Do logic minimization. Okay, and in this example, did we use the SOP expression or POS expression? In this example, we did SOP expression. Okay. After logic minimization, then identify what? Help me. Identify the what? The common terms. And then do the logic sharing. Do the logic sharing. And what is my next step? Draw the complete. So these are all the steps. If you want to design a combinational circuit, you identify the inputs. In this particular example, the inputs are A, B, C, D, and the outputs, which is small a, small b, small c, small d, small e, small f, and small g. And then we have 2 to the power 4 combination, which is actually we have drawn the seven K maps, and since we have 7 K maps, so these 7 K, each K map consists of consists of how many entries? 16 entries. Then we do the logic minimization, we draw all and then we find the expression in the sigma form. When we find the expression in the sigma form, then we do the logic minimization. Then after the logic minimization, so when all the 7 expressions, so when we do the logic minimization, after the logic minimization, we have 7 expressions. After the logic minimization, we have how many expressions? We have 7 expressions. When we have the 7 expressions, out of these, we identify the common terms within these 7 expressions. These 7 expressions. Any question? Okay, and then we do the logic sharing, and then we draw the complete diagram. Any question? So this is how we are designing from this series. Should we now proceed now? Yes or no? I'm not hearing. I'm not hearing. If I'm not hearing, so basically it will make me crazy. Yes, Abir. Yes, Anas. Yes, Haura. Do you hear me? Please speak in mic.
Yes, Professor.
Yes, sir.
Yes, Professor.
Good. Please speak because I don't want to talk to the walls. I want to talk to the real people. Please. Okay. So what now we are going to do? So now we are using now. Okay. Now, if you want to design more complex circuits, so more complex circuit can be using the block level method, and we will study this block level method today. Okay. In general block level method, and I will explain this some. We will do something. Okay. Let's say we want to design a 4-bit adder. We want to design a 4-bit adder. Okay, now can you see here? We want to design a 4-bit adder. This is my example. Now we want to design a 4-bit adder. Control C and now Control V. Okay, now if you look at this design of 4-bit adder, this is my 4-bit adder. We have 2 inputs. Okay, so now we want to add these 2 numbers. Please look at here. Look at the block diagram. Look at the regular diagram. This is a 4-bit adder. Okay, now we have 2 inputs. What is my first input? Can you see? Anyone tell me? The first input is X. What is my second input? Can you tell me? Help me. What is my second input?
Y.
Y. What is my third input?
Cn.
Cn is my third input. Yes. Cn is my third input. So these are inputs. So all these things are inputs. Okay. Now we have outputs. This is my output. This is a 4-bit output, which is called as sum, which is S. And now we have another output, which is actually C out. Okay, now if you look at here, how many inputs we have for this parallel adder? How many inputs do we have? Can you see how many inputs?
Two outputs and 3 inputs.
Oh, no, totally wrong. Yes. How many inputs do we have?
9 inputs.
Very good. 9 inputs. Very good. We have 9. We have 9 inputs. Because 1, 2, 3. You can see here 1, 2, 3, 4, 5, 6, 7, 8, 9. How many outputs do we have? So 9 inputs. What are these inputs?
5.
These inputs are X1, X0, Y3, Y2, Y1, Y0, and Cin. And now we have, okay, how many outputs do we have? Yes.
5.
We have 5 outputs. And what are these outputs? Help me.
S3, S2, S1, S0, C out.
Now if you have, now please look at here. Now please, this is very important. So now we have, if you draw this circuit, and the block here, so this is a 4-bit adder. So this is a 4-bit adder. We have 2 inputs, actually X, and then we have the other input is my Y. Another input is now Cin, and my output is now and then my other output is actually C out. So we have, can you see here, now we have now how many inputs? We have 9 inputs. And how many outputs do we have? Help me.
5.
Now we have 9 inputs in our, okay, now $1 million question. $1 million question. How many K-maps do we need?
5. No, 10.
Yes. No, 5. Because we have outputs. We have 5 outputs. We need.
But the number of inputs is more than 4, yeah.
Absolutely. How many? We need 5 K-maps. If you want to solve it in a general way. Okay. Now how many outputs do we have? Inputs.
We have 9.
9 inputs. If we have 9 inputs, so we need to draw the truth table. And if you want to draw the truth table, how many combinations do we have for the inputs? Help me. How many combinations do we have for the inputs?
2 to the power 9.
How many combinations?
512.
7. Can we solve this problem using a truth table approach? So now the question is, so the $1 million question is, can we design a 4-bit adder using truth table approach? Yes or no?
No.
And let's assume. Let's assume this is only a 4-bit adder. Now assume that we have okay, assume we have an 8-bit adder. 1, 2, 3, 4, 5, 6, 7, 8. This is my first input X. And then we have the other inputs 1, 2, 3, 4, 5, 6, 7, 8 Y. And then we have Cin. And then we have the sum. Let's assume my sum is 1, 2, 3, 4, 5, 6, 7, 8. This is my sum. And then we have C out. Okay. How many inputs are here now in this example? We have 8-bit adder. Okay.
17.
Yes, X7 to X0 and then Y7 to Y0. So how many combinations we have? 17 inputs.
2 to the power
We have to
17.
solve 17 combinations. And this 17 combination will be actually equal to 65,536 multiplied by 2 combinations. So can we solve this problem using K-map? Yes or
No.
no?
No.
we want to design these adders, we cannot solve this using the truth table approach. What is now the another approach that we are using? So for this, we are using which approach? Can you see here? Which approach we are using? The block level design method. Any question? Any question? And how
No,
we
sir.
are going to design it? This is very important. Now what are we going to do? Now what we are going to do? So can you see here the 4-bit parallel? So it's SI design. Okay, now can you see here? Now if you look at this truth table. So basically what we are going to do. So now this is my first input. Okay, the first input. So now you can see here this is 5 on 2 for 9 combination. So can you see here now we are now going to solve it here. I'm not going to draw all the combinations. So how many combinations do we have? Can you see here how many combinations do we have?
512.
And the first combination. Now if you look at the first combination, so we are adding this thingy. So the first combination, what do you mean? This is my 0 and this is my 0. When we add 0 plus 0 and C in is 0, my sum is 0 and C out is 0. Okay, now if you look at here, the green color, what is this thing? 5. What is this thing? Help me. 1101. 8 plus 4, 12 plus 1, 13. What is 5 plus 13? 18 plus 1, 19. So now can you see here? This is the code for 19. So this is actually, this will be 19. What is 19? Actually 10011. So this is actually 1, 2, 4, 8, 16. So this is actually 16 plus 2 plus 1, which is actually your 19. So you got all of the possible combinations. Got it or got it? So we cannot solve this method using a truth table approach. Any question? So this is the code for 5. This is the code for 13. So actually, can you see here? And this is 1. So what is 5 plus 13 plus 1 is actually 19. And this is the code for 19. Okay. Now if you look at the last entry, now please look at here the last entry. Now if you look at the last entry, and now I'm using the black color, not the black color. I may use which color? Maybe I can use the blue color. What is this value? This is actually 15. What is this value? It's also 15. And this is 1. So this is actually 15 plus 15 plus 1. What is 15 plus 15? 30 plus 1, 31. And if you go for the output, this code is the code for 31. 1, 1, 1, 1, 1, which is the code for 31. Any question? Any question? Now what we are going to do? Now we are going to design a 4-bit adder using the block level design approach. Now can you see here the 4-bit adder? Now can you see here the 4-bit adder? Now this is my the block diagram of 4-bit adder.
Professor, I have a doubt.
Yes, which where you have doubt?
Like when we made adders before, we had like multiple carries, yeah? One for each bit.
I will explain it. I will explain it.
Okay.
No problem. Please wait for some time. I will explain it. Can you see here? Now what we are going to do? Now we are going to design this pattern. Clear? Can you see? Now I'm making it very thinking. Okay, now we want to design for 4-bit adder. Got it? No. This is visible or not? Is it visible to you, everyone?
Yes, sir.
Yes.
Now what we are going to do? So this is the block diagram of a 4-bit adder. Clear? One minute. Let me make it here. So this is the block diagram of a 4-bit adder. Okay, now we have the first input. And I'm using different colors. And please be attentive. The first input is what? X3, X2, X1, and X0. Any question? And the second input is now Y3, Y2, Y1, and Y0. Any question? Okay. Now we have this input X, which is X, and the second input is Y. And now we have C in, and which is I'm using the black color for C in. Now what I'm going to do, I'm using the blue color for S, which is the output is S. So this is S3, and which is S2, this is what S1, and this is S0. And now we have another output. I call this output as maybe I will call it this color. So this is my C out. Any question? So this is now the block diagram. Okay, now we want to design 4-bit parallel adder. This 4-bit parallel adder can be designed using 4 1-bit adders. So what I'm going to do now in the inside the circle, what I'm going to do. So now I'm using the black color again. Now I'm using 4 1-bit adders. And please remember, all of these are full adders. Okay. All of these are full adders. So now, what are the inputs to any full adder? So we have one A, B, C in, and then what we have this sum and C out. Then we have A, B, C in, and then we have C out and sum. Then we have A, B, C in, and then we have C out and then sum. And then we have A, B, C in, and then we have C out, and then we have sum. Any question? Any question? Okay, now what we are going to do? Now please remember, this is very important. Now the first adder, the first stage, can you see here the first stage? What will go to the first stage? So what will go to the first stage? Now I'm using the green color because now the first stage it will go x0. X0 will go here. We connect this A to x0, then what should we connect? B. B should be connected to what? Help me.
Y0.
Y0.
And what about C in? So can you see here this C in? Now I'm using the black color. So this C in should be connected to C. Any question? Any question? Now we have sum. We have sum. Then we have sum. So what we are going to do? We are connected this sum with what? Where should I connect it? Anyone? Help me. Anyone? Help me.
S0.
Now the carry out from this stage the carry out from this stage. Okay. Now. Any question? Any question? Any question? Any question? You want to ask some question? You want to ask some question?
The sum will go to S0, right? From the first stage.
It will go to S0. Yes, S. Okay. Now, now we have this carry out. The carry out from this stage will go to what? Help me.
Cn.
The Cn of the next stage.
And then where should I connect this A? Where should I connect this A? Help me. Where should I connect this A?
X1.
X1.
So now we are connecting this to X1. So this is my X1. And what should I connect to this A? Help me.
X2.
And then X. And what about this thingy? Now I'm using the red color. What should I connect this to? Here, B. Help me.
Y1.
Y1. Then
Y2.
And then Y2. And the carry out from this. The carry out from this stage will go to the carry in from this. And the carry out from this goes to the carry in from this. And where should I connect this S? Help me. This S.
S1.
And then S2.
S2.
Then
S3.
S3. And please remember, now this is, can you see here? Now this is my, this, and this C out is connected to the minus. Any question? I hope I answered your question now.
Professor, I still don't understand why there's a Cn in the input side.
Oh, now the problem, this is very simple. I will answer your question now. I will answer your question. No problem. No problem. So basically, why we do this? This is very important. You know why? When you are doing any addition, can you see here? This is allowed. Now, why am I going to do this? This is evident in this slides. We want to design 4-bit adder x0, x1, and x2, and x3. Again, let's do. We want to do this thing. We want to do x0 and y0. What will it give me? Help me.
S0.
S0. And the carry out from this will go to the carry in for the next stage, which is actually C1. So this is C1. And it will give to S1, then it will go to C2, then C3, and S2. Got it or not got it? Any question? So can
I
you see
still
here?
don't understand.
Yes. So can you see here? This is actually now this is my C0 here. And this is my what?
Yeah,
C1,
C0.
this is my what? C2,
C2,
and this is my what?
C3,
C3, and this is my what?
C4.
Any question?
No,
Any
sir.
question? Now it's clear? It's clear now?
Yes.
Very good. So now this is how we solve it. This is how we solve it. So this is how we solve it. This is how we can design our this adder. So this is a 4-bit adder. So now what we are going to do? So now we have a 4-bit adder. This is the formula. We have two things, which is Ci plus 1. Please remember, we already did it. Ci plus 1 and Si. What is C8 plus 1? And these are all the things. Okay. So can you see here? This is the full adder. This is C in. This is my first stage, X0 and Y0. And this is the carry in, which is actually C0. It is not C1. And this carry out will become the carry in for the next stage. Any question? And then this carry out will become the carry in for the next stage. And this carry out. Any question? Should we proceed?
Professor, isn't C0 always 0?
Depends on. So it depends on. Let's assume even if we have C in is always 0, so you are adding two numbers. This if you want to make it 0, so sometimes we are making multiple stages, and I'll explain this in my later example. I will not do it later example. So in this case, C in is 0. For the first X0, it is 0.
Okay,
Please
Professor.
hold your question until some time. I will answer your question. Clear?
Yes, Professor.
Okay. Okay. Now we want to design a 32-bit ripple carrier. How many stages do we need? This is the first stage. This is the second stage, and blah blah blah. It goes on. Any question? Clear? This clear or not clear?
Professor, what do you mean by ripple adder?
The carry is rippling. The carry is rippling. The carry is rippling for this is ripple carry adder. So this is ripple from this stage to this stage, this stage to this stage, this stage to this. This is called as a ripple carry adder. So in a
Okay,
ripple
Professor.
carry adder, so it means if you want to design a 4-bit adder, it can be designed using 4 1-bit adders. And if you want to design an 8-bit adder, it can be designed using 8 1-bit adders. Any question?
No,
And the
sir.
carry is rippling from stage 0 to stage 1 to stage 2, stage 3, and there are n stages. Any question?
No, sir.
Okay. Now what we are going to do? Now please remember this is very important thing. So now what we are going to do? So now what we are going to do? So okay, now think of a scenario. Think of a scenario. Think of a scenario. And this is very tricky thing. And why am I going to answer your question now? I'm going to answer your question now. Okay. Now let's assume if you want to design an 8-bit adder. Let's assume you want to design an 8-bit adder. Okay. So what I'm going to do? I'm not going to design an 8-bit adder. I want to design an 8-bit adder. Okay. And let's assume the inputs are 1, 2, 3, 4, 5, 6, 7, 8. The first input it is X, and then we have the second input which is actually Y, and then we have the third input which is actually C in. Okay, and then we have the output. My output is actually 1, 2, 3, 4, 5, 6, 7, 8, which is actually SEM. And now we have some C out. So some C out which is actually the purple color. So this is my C out. Okay, so now please look at here. This can be designed. This can be designed using what? Help me. How many adders are required?
8 full adders.
8 full adders are required. So now we have 8 full adders. So now can you see here? This is my full adder 1. This is my full adder 2. And then we have this full adder 6. And then we have full adder 7. So this is actually A, B, C in, A, B, C in, and S and C out. This is A, B, C in, and this is C out, and this is S. This is we have A, B, and then we have C in, and then we have C out, and then we have S. Then we have A, B, and then we have C out, and then we have C in, and then we have S. Okay, what should I connect this A? Yes, anyone tell me?
X.
X0, and this B, this A.
Y0.
No,
X1.
this A, X1, this A.
X6.
And this A.
X7.
So this is my X7 and X6 and blah 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 until X0. And now we want to connect it to Y. This is my Y7, then Y6 and blah 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 until Y1 and Y0. What should I connect this B? Tell me.
Y0.
Y1 and then Y6 and then Y6. And please remember these are dots. So these are the stages. Okay, this C in is now connected to this one, and this C out will become to connect to this. So this is my C0. This is my what? C1 and blah blah
C1.
blah. And this is my what? C6. Okay, this is my C7 and this is my C8, and this C8 is connected to C out. And this S is connected to what? Help me. S0. This S
S0,
is connected to what?
S1,
S1. And then we have dot dot dot. These are other stages. I'm not going to show it. And this S is connected to what?
S6,
S6. And then what?
S7.
Any question? Okay. Now an interesting thing. Now this is more interesting thing. This is more interesting thing. Okay. Now in this case, we have designed an 8-bit adder using 8 1-bit full adders. Any question? Now we want to design the same for we have the same adders. Let's see, we have the same adder. Control C. And please, I need your attention in this. May be the question in exam, so I need your attention here. Let's assume we want to design an 8-bit adder, and the first input is, let's assume my first input is, this is the first input is black. A7, A6, A5, A4, A3, A2, A1, and A0. And let's assume my second input is 1, 2, 3, 4, 5, 6, 7, 8. So B7, B6, and blah 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 until B0. And then we have the C in, which is the black, not the green color. This is C in. And now my output. Let's assume my output is in red color. So this is actually S7, S6, S5, S4, S3, S2, S1, and S0. And then we have the final C out, which is actually maybe, which color I'm not using. Maybe this color. This color. Okay, this is my C out. But now let's assume we are available with 4-bit adders. Okay, now if we are available with the 4-bit adder, so now what I'm going to do? So now this is my 4-bit adder now. Okay, please remember what is the input to the 4-bit adder. So this is x3, x2, x1, and x0, and then what? Y3, Y2, Y1, and Y0. And then we have another 4-bit adder, which is actually x3, x2, x1, and x0, and then y3, y2, y1, and y0. And then we have C in, and then we have C out. And then we have C in here, and then we have C out here. And let's assume this is actually, this is my, this is S0, S1, S2, and S3. And then this is S0, S1, S2, and S3. Okay, now what should we connect this scene? Yes, what should we connect this scene? Help me. This scene should be connected to this scene. Any
Yes.
question?
No, sir.
Now, what should I connect? Y0. Y0. Why should 0 should be connected to what?
B0.
Now you got it? Why there was a reason for this should be connected to B0, this is connected to B1, this is B2, and this is B3. Where should I connect to S3? Yes, help me.
A3.
A2, A1, and A0. Any question?
No, sir.
Okay. Now the C out for this will become the carry in for this. Now you know the reason. So basically we use this C in and C out for cascading. So if you are cascading one adder to another adder, so we need C in for that purpose. I hope I answered your question now.
Yes, sir, I got it.
You got it? Okay. Now where should I now connect this X3, X2, X1, and X0? This X3, this one. Where should I connect it? Help me.
A7, A6, A5,
Yeah.
A4.
So now I connect it to A7, then what? A6, then A5, then A4. Where should I connect this Y3, Y2, Y1, and Y0? Help me.
B7, B6, B5, B4.
And where should I connect S0? This S0.
S4.
S0. And this S0.
S4. S5, S6, S7.
And this C out.
C out.
Any question?
No, sir.
Okay, now conceptually. Okay, now conceptually. Now this is very important. Please remember. Now this is now the moral of the thing. So now we are going to have. So let's assume. So now I can say. Okay, let's assume if we want to design. So we want to design a 16-bit adder. So it can be designed using what? It can be designed using what? Tell me. Using
16 full adders, 1 bit full adders.
1 bit full adders. Am I right? Yes.
Yes.
Any question?
No, sir.
Okay. No, this is I'm not finished. It can be designed using what? 8.
2 bit full adders.
No, not full adders. Full adders. Please remember, full adders is only 1 bit.
Parallel adder.
Full adder is only 1 bit adder. 1 bit adder. It can be designed using what? 4. How many bit adders?
4 bit adders.
And it can be designed using what? Tell me.
2 8-bit adders.
Any question? And this method is called, okay, now what we can say. So this method, so now what I'm going to do, so now I'm again inserting a text box. So with my text box here. This is a text box, yes. This method is called as what? Tell me.
Block design.
Block design approach. Any question? Now this method is called as the block design approach. Now what we are going to do now? We are proceeding for. So this method is called as the block level design approach. Now what are we going to do? Now, what are we going to do now? So actually, now we want to design. Please remember, we designed a BCD to XS3 code converter. Okay. So now can you see here? So this is called as the block level design approach. Okay. Now what I'm going to do now, we are going to design BCD. Please remember, we designed this BCD to XS3 code converter in our previous lectures. Okay. So now can you see here? Now this is BCD. So now this is Control C, and then what I'm going to do this. Okay. Please remember, now we want to design a BCD to XS3 code converter. Okay. We want to design a BCD to XS3 code converter. So the input is, like, if you look at the system, what is my input? Help me.
ABCD.
What is my input? Input is BCD. So input is BCD. So the input is A, B, C, and D, which is my BCD input. And my output is XS3, which is actually what? W, X, Y, and Z.
WXYZ.
Okay, so all these are valid code or invalid codes? Yes. Can you tell me? 0 to 9.
Valid.
Valid. And from these are what?
Invalid.
Invalid code. Remember? Okay. Now please remember how many KMFs do we have? Can you see here how many entries we have? We have this for 4 input 16 combinations. How many KMFs do we need? Help me.
4 K-maps.
So we need 4 KMFs. In each KMF consists of how many entries?
16.
What's the next step? We draw the CAM map, we do the logic minimization, we need to get level of principle, and we did all in our previous lecture. I'm not going to explain it again. Yeah. Is there any question? Yes. Do you have some question? Yes, sir. I'm not hearing you. Please turn off your mic. Wait. Okay. Any question? Okay. So now you can see here. So we have this. We did it. Okay. So This method we already did in our last lecture. Okay, now what we are going to do? Now we want to design the same BCD to XS3 code converter using a 4-bit add. Okay, now please remember. Okay, now please remember, if you look at the truth table, now if you look at this truth table, if you look at this truth table, what is my input now? If my input is zero, my input is zero. What is my output? Help me. Can you tell me?
3.
Output is 3. If my input is 7 now, what is my output?
10.
10. This is the code for 10. So this is how we design. Now, if you want to design BCD to XS3 code converter using a 4-bit adder, so let's assume we now have a 4-bit adder. This is my 4-bit adder. What is the first input to the 4-bit adder? Help me. Can anyone tell me? Help me. X3, X2, X1, and X0. What is my second input? Help me.
Y3, Y2, Y1, Y0.
What is my other input? Can anyone tell me?
C in.
What is my output now?
S0, 1, 2, 3, and C out.
S0. And then what is my other output? Help me.
C out.
Please remember, this is very important. This is very important. Can we design this BCD to XS3 code converter using parallel 4-bit adder? Yes. How? Can you tell me how can we do that? Yes.
Y is 3 in binary.
Yes. So can you see X3, X2, X1 is actually what? A, B, C, D. So this is my A, B, C, D, which is actually a BCD code. And this is BCD code. Please remember, this is my BCD code. So this is my BCD code. And BCD code is what? A, B, C, D. And what we are adding to it? We are adding 3 to it. Plus 3. So it is plus 3. So plus 3, what is the code for plus 3? 0, 0, 0, 1, 0. So this is actually 0, 0, 1,
0, 0, 1, 1, yeah.
Yes, control, sorry. This is 0, 0, 1, 1. Yes, right. 0, 0, 1, 1. And then my Cin is 0. And then my S3, this is my output. What is my output? S3, S2, S1, S0. So my output is now what? So basically my output is actually, help me. Can you help me? W, X,
X, Y,
Y.
Z.
Okay. Is there any other method to design this BCD to XS3 code converter using the 4-bit adder, but using a different method?
2 2-bit adders.
Anyone solve this question, he may get 1 bonus mark. This is very important. So anyone will solve this question, he will get 1 bonus mark.
Can you
Now
use
this is
2
my
2-bit adders?
BCD.
Can you use 2 2-bit adders?
No. I will use. You can see here. I will still use a 4-bit adder, but using a different method. If anyone will solve this question, will get 1 bonus mark. So this is my X. This is my X3, X2, X1, and X0. Then we have Y3, Y2, Y1, and Y0. And then we have the sum, which is actually S3. Sorry, Control G. Anyone who will solve this question will get 1 bonus mark. S2, S1, and S0. Then we have C in, and then we have the purple color, maybe C out. Yes. How can we design it? Using a different method, but you are using a 4-bit adder. Anyone? Can I write something like this? What is my XS3 code? BCD plus 2 plus 1. Can I write? Because 2 plus 1 is 3.
Yes.
Yes. What should I write here? So different methods. So what I'm going to do? So now what I'm going to do? This is my BCD code. So then I'm now using an alternate method. So now this is my BCD code. What I'm going to do? So now I'm putting A, B, C, D here. Now because it's a addition is commutative. Its addition is commutative. Plus 2 plus 1. This is my 2. So this is equal to 2 is actually 0, 0, 1, 0. So 0, 0, 1, 0. Any question? And this is 1. So I put C in is 1. And I put a VCC here. Any question? And what should I connect? S3. S3, yes. Where should I connect
X3,
S3? Help me.
S3 should be W.
Any question? So this is another method. This is another method to design a BCD, to implement a BCD to XS3 code converter using a 4-bit adder. Any question? Any question? So now can you
Professor,
see
can
here?
you go
Now,
back to the previous slide?
Good.
Okay, never mind. This is also fine.
Slide. Slide.
The one before this.
Yes.
Yeah, once again, I just want to take a picture.
No, this is all things. I can share all these things. So I can save it. I can save it. Okay, I can save it. I can save it as a different file. And
Okay, thank
I
you,
can share
Prof.
it. I can share it. Working.
Thank you.
Working of lecture number 6. Got it? I can share it. Any question? No problem. If you have this thing, please ask me. If you have this, you want anything. So I'm working of lecture 6. So I will put everything on the slides. Got
Thank you,
it?
Professor.
Don't worry. Taking a lot of time because it's a big file. I could have done it in the end. Is there any question now?
Professor, I have a question about the midterm.
Yes, please go ahead.
Professor, I want to ask if the midterm will be multiple choice questions and like how will it be? Will it be the difficulty of the
No
exam?
multiple choice. No multiple choice because multiple choice I will have like working questions. No multiple choice question.
And we
Okay,
will work
I will discuss
like on the paper
2
and
minutes
send
because
you a
I want.
lecture, or
I will discuss this after 2 minutes. When I will finish. I'm finishing now. Okay. So now what we are going to do now here is, can you see here? Now we have the BCD code. BCD code which color? The red color. Okay. SS3 code which color? The green color.
green color.
And the constant. This is the constant 3. So can you see this is my BCD code, which is actually A, B, C, D. And this is the constant, which is actually 0, 0, 0, 1. And the scene is 0. And then you can say this is COD is unused. And then this is my XS3 code, which is actually WX5. Any question? Okay. So what I'm going to do now.
Professor, shouldn't CN be 1? Oh wait, no, never mind. It's 0,
No,
1.
why scene is 1? Why should change to 1? Scene is 0 in this case because this is 0, 0, 1.
Yeah, because it's 3. Yeah, my
This
bad.
0, 1, 0, this scene will be 1. Got it?
Yes, Professor.
Okay, good. Okay, good. So this is now what we'll do. So now I'm going to do. I'm now going to stop the recording now. Stop recording. So now